Hello and welcome everybody. My name is Schlichtig. I'm a researcher at the University of Paderborn and I will be presenting FUM, a framework for API usage constraint and misuse classification, which is a joint work with Steffen Sassalla, Krishna and Narasimhan and Bodden. Let me start with the motivation that drove us to take a deeper look into API misuses. In our research, we are mainly focused on the secure usage of cryptographic APIs. A recent study by VeraCode has shown that nearly 2/3 of applications contain at least one misuse of cryptographic APIs, and so you can see that the misuse of cryptographic APIs is widespread. The misuse of cryptographic APIs can have massive consequences, even on a personal level. For example, everybody of us probably has a mobile phone, and due to the pandemic situation, we have stored vaccination certificates and even more sensitive data on that. And if cryptography is not applied correctly, this could lead to data leakage or even worse. That is why we are working on facilitating the secure integration of cryptography into code. Therefore, we have developed Copycrypt, a static analysis tool for detecting the misuse of cryptographic APIs in Java code. Let me explain how this works. So generally, an API is developed and designed by an API expert. The API is then used by developers in the development of their own code. For the analysis with Copycrypt, we then use our domain-specific language Crystal, where we define rules on how to correctly use the API. The static analysis tool Copycrypt then consumes the Crystal rules and uses them to configure its analysis and can then use that to analyze program code. After performing the analysis, Copycrypt reports all the misuses that it found. We call this the allow listing approach. The Crystal rules specify which usage of the API is correct, and Copycrypt reports every usage that does not conform with the rules. This works really well. So we were interested in whether we can use Copycrypt to also detect general API misuses other than cryptography. We then tried to specify Crystal rules for other common APIs. We found out that it does not work, and this drove us to take a deeper look into why it doesn't work. Therefore, we looked into the theory of general APIs and their misuse, what they are and how they work. As I said, we realized that we needed to have a better theoretical understanding, and this led us to our two research questions. First of all, we wanted to get to know the theory and literature behind API misuses, and our research question 1 therefore is, how is the term API misuse defined, delimited, and made tangible? And the second research question focuses on having the classification framework that we can use to then analyze which API misuses Copycrypt can detect, or how we can improve Copycrypt. So to answer research question 1, we performed a literature review. We used terms like API misuses, misuse detection, library misuse, and similar ones in the scientific libraries IEEE Explorer and Google Scholar. We compiled a list with inclusion and exclusion criteria and snowballed the findings until we gathered our literature. And then for the second research question, we used the results of our literature review to derive definitions and consequently derived a new framework we call FUM from the results. Our literature review revealed several terms around API misuses, and in this overview I want to explain the different terms that we found and how they correlate to API misuses. First of all, we have API directives. They are natural language statements that describe how an API should be used optimally and correctly. API directives are either documented or they are implicit. For example, if the API's domain takes them for granted knowledge or accepts them as true. In general, API directives take the perspective of the API designer or expert and are imposed onto the API by the designer or expert. Next, we have API usage constraints, which are a subset of API directives. API usage constraints are restrictions that limit the allowed usage of an API. These constraints cannot be enforced with the means of programming languages, like correct typing, which is checked by the compiler, but they must be actively observed by the user of the API. Lastly, we can now see API misuses as and define them as violations against an API usage constraint. Such a violation leads to misbehavior of the API, for example, errors, crashes, or vulnerabilities. Overall, we use these results to derive 4 definitions, the last one for API misuses as a violation against an API usage constraint I just stated, and thereby we answered our first research question. With the overview of our definitions from research question 1, the next step is answering our second research question for a classification framework. We have derived our classification framework from 23 different studies. We define our framework based on API usage constraints because as soon as an API does not define API usage constraints, the API cannot be misused. Hence, it is more natural to look at different types of API usage constraints instead of API misuses. However, in the practical application of the framework, one might still use the terms interchangeably. I will now present FUM, our framework for API usage constraint and misuse classification, which is localizing each API usage constraint type to parts of a method call. A method call consists of the return value, the API object or class on which a method is called upon, and the argument or arguments that are passed in the method call. I will now only discuss some API usage constraints, constraint types or FUM types due to time. First of all, we have the post-null check, which are rather implicit constraints, which requires null check to avoid runtime errors with null pointer exceptions. Next, we have the method call sequence where several methods have to be called upon an API object in order to complete a correct usage. Certain API objects must be used in a predefined way with respect to method calls. In other words, a method call sequence is imposed on the API object, which is also known as protocol. Then we have the controlling method call. They are constraints that describe that a certain method may only be called if a certain condition is met. This condition then is checked by the controlling method call. For example, the controlling method call takes place in a control structure so that a certain method call is only allowed if the state of the API object allows it. Next, we also have the pre-null check, which is more or less the same as the post-null check, only in this time for arguments of a method call, where the method called requires the value not to be null, to be passed. Lastly, I want to present exception handling, which you can see are constraints that can be imposed on all parts of a method call. Such a constraint describes situations in which an exception handling is necessary and must be considered by the developer in order to not get into situations of an uncalled exception, in other words, to also avoid program crashes. Furthermore, you can see in the bigger picture that there are also high-level constraints. These are constraints that are happening everywhere on a method call that are not part of any of the other types yet. With this, we have answered our research question number 2 by introducing FUM. Coming back to our motivation of using Copycrypt for the detection of general API misuses, we then used FUM to perform a case study where we analyzed which FUM types can be specified with Crystal and therefore are detectable by Copycrypt. We derived API misuse samples from two data sets with code samples. These are the MuBench dataset and the most common API misuses in bug fixing commits dataset. In total, we have 88 API misuse samples, and we then matched them to the FUM types, which you can see on the right-hand side. For the evaluation, we used the predefined process that you can see in the activity diagram here, where we also protocoled all of our results. You can see our total results in the table. The currently column shows that overall 27 of the 88 misuse examples are specifiable with Crystal in the version of our experiment. The next step of our case study was using FUM to identify possible improvements to Crystal to facilitate specifying more FUM types. The analysis of the currently specifiable FUM types in combination with the amount of occurrences of API misuses of samples in our dataset allowed us to target the most influential extensions. For example, as you can see, there are 16 post-null check samples, which currently are not specifiable, but adding a language extension to Crystal may improve this. We therefore decided to propose 4 improvements. We did not cover some types like threading because there were not enough samples in our evaluation dataset. The new language constructs that we proposed can be found in our artifact. They are targeting the FUM types of exception handling, post-null check, pre-null check, and controlling method call. This is also not surprising because Crystal is a domain-specific language for cryptographic APIs, where such FUM types are typically not required. By implementing those proposed improvements, theoretically 92% of all API misuse samples of our dataset now will be detectable. However, for some FUM types, there were not enough samples in the dataset for proper evaluation, for example, for synchronization and threading. And overall, for larger evaluation and the further development of Crystal and Copycrypt, a bigger dataset would be needed, and therefore a large-scale study on API misuse types is reasonable. To summarize, in this presentation, we've presented the findings of our literature review and the derived definitions around the term API misuse. Then we have introduced FUM, our framework for API usage constraint and misuse classification, which localizes API usage constraints to method calls. Lastly, we've presented the results of our case study where we showed that FUM can be applied to analyze the capabilities of an analysis tool and help to derive targeted improvements. These are the sources of the 2 datasets that we used to derive our dataset of misuse samples for the case studies. Thank you for your attention. If you have any questions or are interested in discussions or collaborations, this is my contact information. Just write me an email. I'm happy to hearing from you.